Hi, today we will be discussing about string theory. Let's know what is string theory, who invented it, what is the importance of this theory, how is it related to gravity. In this episode, we will be discussing about some of the points of string theory, and please subscribe to our channel and hit that bell icon to get notifications at the earliest hour possible. Let's get started.
In physics, string theory is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. String theory describes us how these strings propagate through space and interact with each other. On distant scales larger than the string scale, a string looks just like an ordinary particle with its mass, charge, and other properties determined by the vibrational state of the string. In string theory, one of the many vibrational states of the string corresponds to the gravitation, a quantum mechanical particle that carries gravitational force. Thus, string theory is a theory of quantum gravity. String theory is a broad and varied subject that attempts to address a number of deep questions of fundamental physics. String theory has contributed a number of advances to mathematical physics, which has been applied to a variety of problems in black hole physics, early universe cosmology, nuclear physics, and condensed matter physics, and it has stimulated a number of major developments in pure mathematics. Because string theory potentially provides a unified description of gravity and particle physics, it is a candidate for a theory of everything, a self-contained mathematical model that describes all fundamental forces and forms of matter. Despite much work on these problems, it is not known to what extent string theory describes the real world or how much freedom the theory allows in the choice of its details. String theory was first studied in the late 1960s as a theory of the strong nuclear force before being abandoned in favor of quantum chromodynamics. Subsequently, it was realized that the very properties that made string theory unsuitable as a theory of nuclear physics made it a promising candidate for a quantum theory of gravity. The earliest version of string theory, bosonic string theory, incorporated only the class of particles known as bosons. It later developed into superstring theory, which posits a connection called supersymmetry between bosons and the class of particles called fermions. 5 consistent versions of superstring theory were developed before it was conjectured in the mid-1990s that they were all different limiting cases of a single theory in 11 dimensions known as M-theory. One of the challenges of string theory is that the full theory does not have a satisfactory definition in all circumstances. Another issue is that the theory is thought to describe an enormous landscape of possible universes, which has complicated efforts to develop theories of particle physics based on string theory. These issues have led some in the community to criticize these approaches to physics and to question the value of continued research on string theory unification. In the 20th century, 2 theoretical frameworks emerged for formulating the laws of physics. The first is Albert Einstein's general theory of relativity, a theory that explains the force of gravity and the structure of space-time at the macro level. The other is quantum mechanics, a completely different formulation which uses known probability principles to describe physical phenomena at the micro level. By the late 1970s, these 2 frameworks had proven to be sufficient enough to explain most of the observed features of the universe, from elementary particles to atoms to the evolution of stars and the universe as a whole. But still, in spite of these successes, there are still many problems that are still unsolved. One of the deepest problems in modern physics is that the problem of quantum gravity. The general theory of relativity is formulated within the framework of classical physics, whereas the other fundamental forces are described within the framework of quantum mechanics. a quantum theory of gravity is needed in order to reconcile general relativity with the principles of quantum mechanics. But difficulties arise when one attempts to apply the usual prescriptions of quantum theory to the force of gravity. In addition to the problem of developing a consistent theory of quantum gravity, there are many other fundamental problems in the physics of atomic nuclei, black holes, and the early universe. String theory is a theoretical framework that attempts to address these questions and many others. The starting point for string theory is the idea that the point-like particles of particle physics can also be modeled as one-dimensional objects called strings. String theory describes us how strings propagate through space and interact with each other. In a given version of string theory, there is only one kind of string, which may look like a small loop or a segment of ordinary string, and it can vibrate in different ways. There are certain paradoxes that arise when one attempts to understand the quantum aspects of black holes, and work on string theory has attempted to clarify these issues. Since string theory incorporates all of the fundamental interactions, including gravity, many physicists hope that it will eventually be developed to the point where it fully describes our universe, making it a theory of everything.
Gravitation, electromagnetism, and also strong nuclear force together in one theory. String theory has so far failed to give up to its promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most useful sets of tools in science. Lastly, I would like to request you all again to subscribe our YouTube channel and hit that bell icon to delve deep into the world of science and know more about the universe. The script is written by Kunal Chakraborty, CEO of Evolution Study, Dr. Chiranjit Pandit, and voiceover by Roop Chakraborty,